Okay, so on day one, we learned to draw vectors. We learned to define what a vector is with a few real-life examples. We also learned how to measure how long they are. You just use Pythagorean theorem. We learned how to find the direction, so we use arctan for that. And then we, on day two, we added them together. We did it algebraically. We add the components to add the numbers. We also saw that you can also add without adding. You can actually put vectors tail to tail and form a parallelogram. The sum comes for free when you draw the diagonal. You can draw a pathway and then connect with a shortcut. That's another way to get a sum. We saw the second method is a little more efficient, and it works great on 4, 5, 6 vectors. We did several homework assignments on it. But we never really talked about addition, multiplication. Like we talked about multiplying a vector by 3, so that just kind of scales the vector to make it 3 times longer, or it stacks 3 identical vectors together. But we never actually multiplied a vector with a vector. Okay? So some people call this lesson Scalar Multiplication. I don't like that name at all. I like to call it dot multiplication. All right? Because I don't want you to think we're learning this again today, where you go v, v, v. That's not what we're learning. We're not multiplying a vector by a scalar. We are multiplying 2 vectors together to get a scalar. Okay? So this is the first time we've ever multiplied 2 vectors together. Okay, for the sake of this lesson, I chose my vectors to be letters, not numbers. So instead of, u being whatever, 8, -9, and v being -3, 2, like we've been using, we're just going to go generic and just call it ux, uy, and vx, vy. But those are just numbers, if you think about it. They're just 4 numbers. Okay, we are seeking to define a product, u times v, and we would like it to give us a number in the end. Okay? We also would desire for u squared, that would mean u times u, to be some meaningful answer. Okay? It would be really nice if we could get u times u to give us the square of the magnitude. So here's what I'm saying. Let's say you had the vector 3, 4, right? And you had the vector, I don't know, -1, 6. And you want to multiply these together. There are so many ways to combine the numbers with multiplication. You could do 3 times -1. You could do 4 times 6. You could do both. You could do both and then add them. You could do -1 times 4. You could do a FOIL, 3 times -1, 3 times 6. 4 times -1, 4 times 6, like a FOIL sort of thing. And in the end, you're going to get a bunch of numbers, right? And then you kind of crush them all together into one number. Maybe you're supposed to add them or subtract them or multiply them or divide them. What are we supposed to do to get a number in the end? Well, we'd like the answer to be meaningful. Okay. And taking v out of the picture, it'd be really nice if multiplying u with itself, if multiplying u times its own self, if this could somehow give us something that's sort of meaningful, it would be nice maybe if it just came out to 25, which is, 5 times 5, since those are the magnitudes. So I know it sounds like we're inventing our own mathematics here, but we would like to create a new method of multiplication, and we would like it to give us meaningful answers in special cases. So like a special case would be multiplying a vector to itself, u times u. I would love for this to come out to be 25, and there's only one way to really make that happen. So we're going to create a mathematics formula that multiplies 2 vectors, and when you multiply the vector 3, 4, and 3, 4, it actually gives you 25, which is also magnitude times magnitude, 5 times 5. Okay? So I know it's a very awkward start to a lesson, but we desire to create a method to multiply 2 vectors to create a number, and it must be a number that is meaningful, especially in the case we multiply a vector unto itself. Wow. Historically, this is how things pan out. And so here's the questions that come up when you create this method. Let's say you wanted to multiply a times AB and CD. Well, which values from the first vector would you multiply with the values in the second vector? Should you do a FOIL product? Should you multiply just A and C and then B and D? Or maybe we should multiply A with D and then B with C. after we get these numbers, AD, BC, AC, and that sort of stuff, what do we do with those numbers to crunch them together and form a final single numerical answer? So these are just logical questions that the person would have if they were trying to invent the math. In other words, should we end up with AC plus BD plus BC plus BD? That'd be like the FOIL. Should we just get AC plus BD? Maybe it's AC minus BD, or AD plus BC, or AD minus BC, or AD minus BC over 2. Or how about something really goofy like AD plus BC plus BD plus AC all over root 5 pi? No one's calling the shots. We are. We are calling the shots. We are going to control this situation. We're going to make a meaningful product, especially U times U equals 25. Okay? Okay, so let's look at what we want in the end. We really want U squared to create magnitude U squared. Like I said, we want 3, 4 times 3, 4 to give us 5 times 5 in the end. So let's write down the vector AB, and then let's try to find its magnitude. So what is the magnitude of vector AB? The square root of what? A squared plus B squared. What would squaring that give us? So if we squared that, what would that give us? A squared plus B squared. So we want we want vector AB times vector AB to give us A squared plus B squared. So it looks like we need to basically go this route. A times A plus B times B. In other words, we're not going to FOIL. We have decided when we do our multiplication, we will only multiply the firsts with the firsts and the lasts with the lasts and add them. Why? Because FOILing gives us something, gives us a number, but it's not as meaningful. This will give us a meaningful product, especially when we multiply AB by itself. We will automatically get AB's magnitude times itself. So the classic example, the one I just showed you, this is the real way to really grasp it. We wanted to multiply 3, 4, and 3, 4. There were many number pairs we could try to come up with, but what would be really nice is, since this has magnitude 5 and this has magnitude 5, it would be nice if this just came out to 25. So we actually decided to do the 3 times the 3 and the 4 times the 4 and add them. So instead of FOIL, it's just F and L, firsts and lasts. So it's not FOIL, it's just full FL. First, last, add. Okay? So now we have created dot multiplication, it's called, or finding a dot product. So we call this, this is what it says at the bottom. It says, we call this finding a dot product or dot multiplication. Some people like to call it scalar multiplication and scalar product. I don't like that because it reminds us of what we learned. It makes it sound like it's this sort of thing. It's not. It's not this. That's why I won't call it scalar multiplying. A lot of teachers do, but I won't call it that. I'm going to call it dot multiplying. That way you won't be confused. It's not multiplying a vector by a scalar. It's multiplying two vectors to create a scalar, a number. Okay, so you're like, okay, Mr. Shore said that would be very meaningful, but I don't know how it's meaningful. I see that he created a convenient way to multiply, but I don't see what this would mean in general. Like, for example, if you did U times U, yeah, that makes sense, but what happens if you did U times V? What does the answer mean then? Okay, so let's try it real quick. Let's find the dot product. It's really, really easy. Multiply firsts with firsts, lasts with lasts, and then add them together. You should get a negative number. Try it real quick. Go ahead. Firsts with firsts, lasts with lasts, and okay, so you should have gotten negative 11. Raise your hand if you got negative 11. Okay, because you're doing 1 times the 4, and then you're doing the negative 3 times the 5, and then you're supposed to add them together. That's how dot multiplying works. And so this just becomes 4 minus 15. Okay, so Mr. Short said that this would create a meaningful answer. But what does it mean? What is negative 11? Is it the length of the first vector? No. Is it the length of the second vector? No. Is it the product of their lengths? No. Well, what is it? We're going to find out. It's going to be a little harebrained, but it's quite meaningful. I will tell you this, that negative is a clue. It helps us understand how the vectors are aiming one to another. So remember, these are arrows, right? They either kind of point towards each other or they don't point towards each other, right? You know, that's how arrows are. You draw two arrows, they're either kind of pointing in the same direction or they're not, right? Well, that number, that negative 11, tells me something. It tells me that they're not really pointing in the same direction because it's negative. So we're going to see that in a minute. And we'll be very clear why it's negative 11 and not a negative 16 or whatever. Okay? All right. So it says here, first find the dot product, and we did. Okay, so that's done. Now, draw the vectors u and v tail to tail. Draw the vectors u and v tail to tail. You're going to have to kind of start not at 0, because you're going to have to go down 3. So, I don't know, let's just start where we want, right? Why not start right here? Okay. So, let's draw vector u. It's right 1, down 3. Doesn't really matter where you start, right? That's vector u. And vector v is 4, 5. Now, hold on. Don't connect it to the head of u, though. It says draw the two vectors tail to tail. See that? Tail to tail. So be careful. Make sure you always follow the directions. So starting again at this point, we're going to go right 4, up 5. And this is vector v. Hey, I was right. They don't really point in the same direction. They're almost sort of opposite each other. By the way, that's what the negative meant. So we'll see that in a minute. Okay. Well, anyway, it also says now to label the angle theta between the tails. Label the angle theta between the tails. So let's see. Let's use a black pen for that. We're talking about this angle here. There we go. All right. So we drew the vector. We found the dot product. Drew the vectors u and v. Labeled the angle. Next, draw v minus u by completing the triangle? What are they talking about? Do you guys remember when we did our first geometric addition method and I had you draw a parallelogram? Remember that? Okay, let's do that again real quick. Put your pen at the head of v. Put your pen at the head of v. Okay. Go right 1 and down 3. Use that as the fourth vertex and create yourself a parallelogram. Okay? We know that the diagonal of the parallelogram represents the sum of u and v. Remember that? So if you draw the diagonal, don't draw it, but if you draw the diagonal, it means u plus v. That was one of our lessons, day 2, part 1. Right? Does anyone know what happens if we draw the other diagonal? It's not u plus v. It's u minus v, correct. Or v minus u, depending on which way you aim it. Okay, so we hadn't really talked about that too much, but it turns out that if you want to draw, if you want a convenient, quick way to draw v minus u, instead of thinking parallelogram, just finish the triangle here. See the blue and red? Draw one more segment to make a triangle. Aim it at v. So aim it upwards at v, and it's called v minus u. So like this. That's a quick and easy way to graph v minus u. Just think of it as, I'm going to finish the triangle, and I'm going to point it at v. That's v minus u. If you want u minus v, then you quote-unquote finish the triangle and aim it at u. So if you want v minus u, aim it at v. If you want u minus v, aim it at u. So in other words, you don't need a parallelogram. If you're going to just find v minus u, finish the triangle by drawing towards v. And if you want to draw u minus v, then finish the triangle by drawing towards u. Notice, this is when our vectors are tail to tail, the blue and the red, okay? So be careful not to. Anyway, there's a quick and easy way to get your v minus u. Let's label it v minus u. And now that we have a triangle, I just can't resist the law of cosines. You're probably thinking to yourself, I could totally resist using the law of cosines. I hate the law of cosines. But you have to admit, we do have a nice SAS situation here. We have three givens, right? Basically, red, blue, black. They form a nice SAS pattern here. And then we've got this third side over here. Actually, it's probably the theta that's unknown. It's the three sides are known. It's an SSS, I should have said. But that's basically law of cosines. Let's write out the law of cosines. So I'll write it first using just the old method you remember. It goes a squared plus, actually it goes like this. Make sure I give you the version you remember here. I think it goes something like this. Okay, so remember this was like c squared equals a squared plus b squared minus 2ab, right? Cosine c. Does this look familiar? Okay, it's just the good old law of cosine. I've color-coded it so it matches our triangle. Okay, so let's sort of, I guess, apply law of cosines to our letters. So we don't have a, b, and c. We have u, v, and v minus u. We don't have angle c. We've got angle theta, but it's the same thing. So it's going to get a little complicated. Instead of a side c, we have a side v minus u. It's all color-coded there for you. Instead of a side a, we have a side u. And that goes here and here. And instead of a side b, we have a side v. Okay, so they asked us to write the law of cosines specific to our situation. Okay, notice the little magnitude bars popped up everywhere. That's because we don't really want, this is a triangle and the sides are not ABC, they are magnitude of u, magnitude of v, magnitude of v minus u. They're lengths, right? So that's why I put little double bars in everywhere. It's a little confusing, but at least it's fill in the blank. Okay, now you're going to plug in your numbers. Hold on. We know that this vector is 1, negative 3, right? We know that this vector is 4, 5. We never found the green one. What is blue minus red? So blue vector minus red vector. Just do an algebraic subtraction for me. So what's 4, 5 minus 1, negative 3? What is it? 3, 8, yes. Okay, good. So our green side is going to be basically square root of 9 plus 64. Square root of that. And then, since it's side c squared, there's also a square on there. For side A, it's a 1 and a 9 because I'm squaring the components. So it's 1 squared plus negative 3 squared, square root, and then squared. So that's what's going on here. And then the blue side would be 4 and 5. So it's kind of a notational nightmare. Like there's just tons of letters and writing and it's confusing. But it really is just me measuring the three sides so I can perform the law of cosines. In other words, we have square root of 73 on the left, square root of 10 on the right, square root of, this should be a 25, right guys? No, this should be a 16 plus a 25. Mr. Shore is getting sloppy. This should be, I'll highlight my mistakes so you can easily find it. Mr. Shore wrote that wrong and he wrote that wrong. Those should be 16 and 25, not 4 and 5. Okay, so I was going to put a 41 here, and this is a 10, and this is a 41. There we go. Okay, so we get 73, 10, 41, 10, 41. And now you can see that we're on our way to finding theta. All right, right, so far, so good. If we're going to solve for theta, then we need to sort of isolate theta, right? So we're going to try and bring all the constants to the left side, maybe, huh? Let's do that. So scroll down a little bit. Let's see, where did I get to? Oh, yes. I was right here. I had 73, and this was a 10, and this was a, except that was red, so Mr. Short messed that up. This is 73, 10, 41, right? Okay, 10, 41. All right. You can tell that Mr. Short now has just the negative 2 rad cos theta by itself, so I think I moved the 10 and the 41 over. So this is just negative 22 equals 2 root 10, or negative 2 root 10 root 41 cos. It's a negative, excuse me, it's a positive. We subtracted both 10 and 41 from 73. Yeah. What happened on the next step? What did Mr. Short do? Divided by negative 2, right, obviously. So divided by negative 2. Then we have a 10 and a 41. And then what did Mr. Short do on the next step? Divided by the rads, right? So negative 11 over root 10, root 41. I hear the calculators. Wait. Negative 11? Negative 11? Where have we seen him before? I hear some O's. Didn't we just have a negative 11 at the top of the page? What was it? The dot product just popped up. Don't type yet. You'll lose him. You'll lose the information. This formula is telling us something, isn't it? There's a shortcut to this problem, isn't there? This is the dot product that we found earlier. This was u dot v. You see? And these two things on the bottom aren't mysterious either. We know what these are. What's rad 10? Magnitude of vector u, correct. And what's rad 41? Yes. So I think we've got ourselves a formula. That's rad, or excuse me, that's a magnitude u. That's magnitude v. Okay, now you can go ahead and give me the angle if you want to type it in, okay? Make sure it's in degrees mode. Well, at least we gleaned some truth before we just start punching in the numbers. We learned something there, I think. We might be able to use it next time. What's the angle? Don't forget that negative on top. We don't need everybody to get it. We all know how to type. Can somebody shout out the angle? Because I don't remember what it is. I know it's more than 90. 122.91. Let's say 123. On the homework or the quiz or the test, I might ask you for extra accuracy. So I might have you write 122.915 or whatever it is. Okay? But for now, let's just write 123. What is that thing? Go back to your picture. What is that angle? That was our theta in the picture, right? Remember, our vectors look like this, and then there was this theta between them. Remember that? I think that's the tail-to-tail angle. You know, if this is a generic vector u, and this is a generic vector v, and you seek to find the angle between them, that's what we just found, you see? Okay, interesting. 123. Look at your last two lines of work. We kind of already peeked at it. Can you create a general rule? So here's the situation we had. We had a negative 11, we had a rad 10, a rad 41, and this was equal to cosine theta. That top number was u dot v. How long did it take you to find u dot v at the top of this page? Yeah, like 10 seconds, right? 15 seconds. Super easy. So easy. these are the magnitudes of u and v. How long does it take to find a magnitude of a vector? Not very long. Square root of 1 plus 9, square root of 25 plus 16. That's not hard. So next time we're going to use this. And it's going to go a lot faster. No more law of cosines, folks. What is our generic formula? When you want to find the vector, the angle between two tail-to-tail vectors, just use this. Inverse cos u dot v over magnitudes I meant to write double bar u, double bar v. Okay, so remember I was saying yesterday, this is all very foreign language. If I had just written this on the board at the beginning of the period, you'd have been like, what in the world? You know? And at first you might be like, oh yeah, u times v over magnitude u, magnitude v. I got it, right? Because a lot of teachers do that. They just put the formula on the board. But listen, you wouldn't have known what this symbol meant right here. See the little dot? You wouldn't even know what that meant. You wouldn't know that it means first times first plus last times last. You wouldn't know that. And if I told you that, you wouldn't know why we have that. I mean, you just either run the risk of being that extra student who sort of passes pre-calc and is cool with that, or you could be that next person who really understands it and can develop the next branch of math. Okay? We created the dot product out of necessity, and we just saw our first use of the dot product. It finds the angle between any two vectors. Now, if you have vectors in three-dimensional space, right? So Mr. Shore's got a marker sticking out of his nose, pointing one direction, and a marker sticking out of his ear, pointing a different, or ruler sticking out of his ear. There's an angle between these vectors. I can find it. And none of it's hard. Dot product's a piece of cake. First plus last. No big deal. Magnitudes. Square root of 1 plus 9. Square root of 16 plus 25. Got my calculator, cos inverse of the ratio. Very cool. Okay, and we proved it, so you can feel totally comfortable using it. You were part of that process. Okay, now let's look at these little conditions here. These little conditions. Did you notice that we got an obtuse angle on that last problem? Okay. I actually predicted that before we started the problem. Do you remember I said this negative 11 means that vectors are pointing opposite directions a bit? Remember I said that? Okay, how did I know that? So let's talk about that for a minute. So the formula that we have looks like this. Going right at the top of this side of the page also, okay? Because you should have flipped the page over. But I'd like you to write the formula here. This is what we're trying to study. Isn't it true that Mr. Store's going to write it on the side over here. I need a little more space. Isn't it true that magnitudes are always positive creatures? Isn't that true? Okay, so this thing on the bottom, oops, magnitude u, and magnitude v. These little guys on the bottom, these guys are always positive. Positive, positive, always. In other words, the denominator here is always going to be positive. It's a length times a length, right? But that top there, that top is going to be sometimes positive and sometimes negative. Okay? It all depends on firsts plus lasts. Sometimes it'll give us a positive result. Sometimes it'll give us a negative result. The dot product could be positive or negative. Actually, it could be zero also. That can happen. Okay? So the top here is going to be positive or negative. It depends. So think with me here. Let's say that we were dealing with case 1. And theta was inverse cosine of, and then these are positive down here. And then let's say the dot product was a positive number. Okay? What is positive divided by positive and positive? Positive. And when you apply an inverse cosine, you're looking for the angles that have a positive cosine. Well, which quadrant is that? Think about the 4 quadrants, right? In inverse cosine, you're only allowed to use the top 2. See my arm? Okay, so the cosine would be positive because everything is positive. So that would naturally mean it's not quadrant 2, it's quadrant what? 1, correct. In other words, the angle theta is what? Between what? 0 and 90. In elementary school, we call that a what angle? Acute. Right. So, I know, so cute. So, I'm getting excited about this, but what this means is the cosine is positive, which implies that theta is stuck between 90 and 0. In other words, it's an acute angle. So under what conditions, then, would theta be acute? How would you describe the dot product? Remember, the dot product is right here. Under what conditions will we get acute angles between the two tails? When the dot product is what? Positive, that's right. So when the dot product is positive, they form a nice acute angle. Okay? So let's write that. When the dot product is positive, theta will be acute. Okay? Let's look at case number 2. In case number 2, remember the denominator is always positive. But imagine if this was negative. The dot product is negative, let's say. Well, what's negative divided by positive times positive? Negative, right. So when you inverse cosine, don't play with your phones right now, okay? We're learning. If you do inverse cosine of a negative, is that quadrant 1 or is that quadrant 2? That's quadrant 2, where all the cosines are negative. Right. So this forces the angle to be between 90 and 180 now. Also known as a what kind of angle? Obtuse. You see? But whose fault is it that it's obtuse? The dot product. You got it. The dot product. When the dot product is negative, theta will be what, class? Obtuse. This is how I knew instantly that our two vectors, u and v, even before I drew them, you guys told me the dot product was negative 11, and I knew instantly that they were aiming sort of away from each other. It's because I knew that angle was obtuse between the tails. Does that make sense? So the dot product is meaningful. It is meaningful. Okay? It provides us with a way to quickly judge whether vectors are sort of aiming in the same direction or if they're sort of opposed to each other. Okay? There's a typo here. It says describe the vectors. Can you guys do me a quick favor? Change that to describe the dot product. We've been describing the dot product so far. Okay. Now, think with me. We had case 1 and case 2. In case 1, the numerator was positive. Right? The numerator was positive. And we got an angle between 0 and 90. In case 2, the numerator was negative. And we got an angle in quadrant 2 between 90 and 180. Under what conditions would theta be not in quadrant 1, not in quadrant 2, but right smack between them, 90 degrees? This would not be positive. It would not be negative. It would be what? 0. This is case number 3. If it's neither positive nor negative, then naturally it's 0. If it's 0, then it's not quadrant 1 or quadrant 2. It's what? Right between them. Theta would be 90. So how would you describe the dot product? How would you describe the dot product in this situation? Why is theta 90? Because the dot product was 0. Correct. So when the dot product is 0, theta will be 90, or will be a right angle. Okay, good. Okay, that only leaves us with one last possibility. Either the vectors are pointing acute, or they're pointing obtuse to each other, or they're pointing 90 degrees to each other. But there's one more possibility. What if the vectors are pointing angle to each other, we know that the dot product's negative. We also know when the dot product's 0, that means they form a perfect 90-degree angle. But what about the case where they're both pointing the same direction? Like this picture or this picture. In the first picture, theta is 0. If you put those two vectors tail to tail, you're not going to have an angle between them. And if you put those two vectors tail to tail, they're going to form a pair of like a pair of opposite rays. See what I'm saying? So when you put these together, in the first picture, you're going to get this. They're overlapping. And in the second picture, you're going to get this. In the first case, the angle between them is 0 because they're literally right on top of each other. In the second picture, the angle between them is 180. Right? Okay, so this time it says describe the vectors. What do you notice about the two vectors in my first diagram? They're pointing what? In the same direction. Correct. So this is a little different. This is if theta equals 0 degrees, it means the vectors point the same direction. And if theta equals 180 degrees, how would you describe the direction? It means the vectors are pointing what? Opposite directions, right. The vectors point in opposite directions. See, I could have just told you all of this at the beginning of class and saved 45 minutes, but you wouldn't understand any of it. You would just know it. And knowledge without wisdom is dangerous. It's just worthless. And in a lot of ways, it's worthless. Sometimes it's helpful to have knowledge, but not to know where it comes from. You'll never really answer those why questions for people. So, okay. Some people use some vocab here that I don't really like. So let me give you one vocab word I do like. Okay. On the theta equals 90 case, some people call the vectors orthogonal. That's a very important word. Okay. And I love that word. Okay. Here's what orthogonal means. Well, what do you guys think orthogonal means? The vectors are orthogonal. That goes with the theta equals 90. What do you suppose it means? They form a right angle. What did you call that in geometry days once upon a time? What do you call that? Perpendicular, right. Okay? Let me tell you why we don't call it perpendicular. Okay? Here's why we don't call it perpendicular. Let's say that this is Tustin Boulevard. Okay? I'll put the other slide up in a minute. This is Tustin, and this is Chapman. You can call these perpendicular. Okay? You can call these perpendicular. There's literally a 90-degree angle between them where they intersect. Okay? But let's say that you draw Bastinchuri, which is a street way up in Brea. Well, it turns out that Bastinchuri does run east-west, and Tustin runs north-south. But I don't think you can call Tustin perpendicular to Bastinchuri, because they never technically intersect. Well, they do, but it's called Rose Drive. So my point is, we should still be able to describe Bastinchuri and Tustin as perpendicular without using the word perpendicular. That's what the word orthogonal means. Okay? When something isn't really touching something else, but they're pointing 90 degrees to each other in space, when you put them tail to tail, it's 90 degrees. Okay? So we have to talk this way with vectors because vectors are rarely touching. This might be vector v over here, and this might be vector u over here. And when placed tail to tail, the angle is 90. But they aren't necessarily placed tail to tail. But one still points east, one still points north. So the word orthogonal means perpendicular without the necessary touching. Okay? So I like that word, and we will use it this year and next. Some people like to use the word here. They like to call this parallel and this anti-parallel. I don't like the words. I don't mind the word parallel. But in my geometry background, because I taught a lot of geometry, these are both parallel situations. Whether your vectors are pointing the same or opposite ways. We would describe those in geometry as parallel either way. So like parallel means this or this. All three are parallel. So I don't like the words parallel and anti-parallel. I would rather just say points the same direction, points opposite directions. So can you guys not use the word parallel in my class? Okay, use the word orthogonal though. Just don't use the word parallel unless you specifically say parallel, as in not anti-parallel. Just say point the same direction. It's better. The word anti-parallel shows up like when you're studying spin diagrams for electrons in their orbital shells. Remember how you have like spin up, spin down, and they occupy the same shell? Maybe you learned that in chem. Okay, that's anti-parallel. They will use that word there because the spin vectors are pointing opposite directions. Okay, but I don't think we need that word in this class. We'll just call it same direction, opposite directions. Okay. Let's go to the next page real quick. Now we have done a lot. We've defined multiplication. We have seen how it can help us find the angle between the tails. And we've also seen how we can do a quick and easy glance at the dot product to decide what it means. What else are dot products good for? Oh, actually, before we do any new stuff, why don't you guys do it now? You try. This might conclude our day, actually. We might not have time for a second application of dots. We might not get to the decomposing part. It's okay. Let's do a now you try, shall we? Your turn.